Chapter 7.5, Systems of Inequalities. So in this chapter, we'll be taking those systems that we've already dealt with, in particular, especially our 2x2 systems for the most part, and looking at what they would look like with an inequality, how does that affect them, etc. So we'll have to know how to graph linear inequalities as well as nonlinear inequalities, and how to use those to sort of check our work. So to begin, a linear inequality in two variables. The equations of the form ax plus by equals c are straight lines when graphed. If we change the equal symbol to a greater than, less than, greater than or equal to, or less than or equal to, we obtain a linear inequality in two variables. So for example, y is less than or equal to 4x minus 5 instead of y equals 4x minus 5. So in this case, we would say a solution of an inequality in two variables is an ordered pair of real numbers, which makes the given inequality true. Each ordered pair solution is said to satisfy the inequality. So for example, here, 3 and negative 3, x equals 3, y equals negative 3, is a solution because if I plug this in, and again, make sure to pay attention to which is x, which is y, so this is negative 3 is less than or equal to 4 times 3 minus 5, like so. So that will be negative 3 less than or equal to 12 minus 5. 12 minus 5 is 7, so negative 3 is less than or equal to 7. That is true. Negative 3 is less than 7. But if I plug in negative 2, 1, I get 1 less than or equal to 4 times negative 2 minus 5. 1 less than or equal to, this would be negative 8 minus 5, which is negative 13. 1 is not less than or equal to negative 13, so this is false. So negative 3 is a solution, but negative 2, 1 is not a solution. Now, how do we know where all of our solutions are, though? That's kind of our goal here, is to find all possible solutions. So we can graph an inequality in two variables in order to find that set. Because it's not just going to be a single equation that's going to answer it. We already have our quote-unquote equations. It's the inequality itself. So instead, we prefer to place our solution set on a graph in order to visualize where our solutions exist. And in order to do that, all we really need to do is graph first our version of the equation of the inequality with an equal sign. Then we make it an inequality. So this line right here is y equals 4x minus 5. Then we test. We test one point on either side of this line in order to see which is correct. So I tested these 2 points and I saw that 3, negative 3 was a solution. And so I colored in everything that was on that side of the line. Had negative 2, 1 been a solution, I would have colored in this side. It's always just going to be one or the other. It's not going to be both. And so we have the solution to our inequality that way. Now, you can use a little bit of logic instead to think, okay, well, y is less than 4x minus 5. So if this is the equation, 4x minus 5, and we want y values less than it, then we're going to be below it. This works in general, you can do that, but it can get a little bit confusing, especially when we get into the nonlinear inequalities. So it's generally safer just to pick a point and test it instead of trying to logic it out. But having both, thinking it out both ways, okay, y is supposed to be less, so I should go down, is a good thing. Like, you should think that as well. So how do I, just in general, steps to graphing a linear inequality? So start by replace the inequality symbol with an equal sign and graph the corresponding linear equation. So here we have y equals 2x minus 3. What does that look like? And I'm not going to go through all the steps to graphing our lines because, again, that's a topic that was covered heavily in algebra. So if you're rusty on it, then it is something you should look back and review, but it is not something I will be covering here. So I'm going to assume that we know how to graph this line from here on out. So y equals 2x minus 3. We've got slope of 2, y-intercept of negative 3, that's going to look like the following. So here's this line. Now, make a note. We will draw a solid line if the original inequality contains the or equal to part. So the less than or equal to or the greater than or equal to symbol. So if we are or equal to, it's a solid line. We will instead use a dashed line if the original inequality was just less than or just greater than. So in this case, the original inequality was y is greater than, not or equal to, so we will be using a dashed line for this problem. Next, we choose a test point from one of the half planes. Don't choose a point that is on the line, this will not work. You have to choose just a point that's on one of the half planes. Generally, if my line doesn't go through 0, 0, that's the point I'm going to pick because it's the easiest one to plug in. But you can pick any point you want. So, I'm going to pick 0, 0 though. Because once again, if it's not on my line, it's the easiest one to use. So I plug in 0, 0. What happens? Well, when I plug in 0, 0, that's going to replace my y and my x. So it'll give me 0 is greater than 0 minus 3. Or in other words, 0 is greater than negative 3. And you ask yourself, is this a true statement? Is 0 greater than negative 3? On my number line, 0, negative 1, negative 2, negative 3. Yeah, 0 is definitely greater than negative 3. So, this is true. Check. And that means this is the side I'm going to color in. So if it is a true statement, I color in that part. If it were a false statement, I would just color in the other part. It's generally a good idea to check a point in the other part just in case you made a mistake, but generally speaking, you're probably safe to just color it in at this point. But you should always check your work. I will keep saying this forever. Just check your work. It never hurts to do so, even if it takes a few extra seconds. Okay. Now, what about if we're working with a nonlinear inequality? So, in order to graph a nonlinear inequality, we're going to use the same steps. Notice I have changed almost nothing here except that instead of graphing the linear equation, I'm just going to be graphing the nonlinear equation to begin with. But everything else is exactly the same. So, start by figuring out how to graph your equation. So here I have x squared plus y squared is greater than or equal to 16. So how do I graph x squared plus y squared equals 16? And this is again something I briefly touched on in the previous chapter, where if you're rusty on how to graph a circle, I'm not heavily going to go over this, but I will very briefly talk about the circle equation here. So circle equation, once again, x minus, I think I used h and k last time, it doesn't matter. It's x minus some letter, y minus a letter squared equals r squared. Sometimes we use ab, sometimes we use hk. I think hk is probably the more universal one, so I'll just go with hk in this case. It doesn't matter, again. So, x minus h squared plus y minus k squared equals r squared. hk is the center, and r is the radius. Like, that's the circle equation. That's the extent to which I'm really going to go over the circle equation. In this case, h and k are both 0, because most of what we talk about in this class, we're just very basic circles, so they're going to be centered at 0. Then, r, well, this is r squared, which means if r squared is 16, then r has to be 4. So we get a circle with radius 4 centered at 0, 0. So again, if it's x squared plus y squared, it's a circle centered at 0, 0. Then square root the radius the radius squared to get the actual radius of your circle. That's the basic steps that you're going to have to take in this class. It's possible you'll see circles that have been moved around and you'll have to identify where the center is, etc. But most of the time, we're just going to see centered at 0, 0 for simplicity's sake. Okay, so I've got my circle here, and I'm leaving it a solid line because this was an or equal to situation. So remember, solid line when it's an or equal to symbol. So this is solid. Then I pick a point. And again, my circle's not going through the point 0, 0. It's centered there, but that's fine. The actual line of the circle does not go through 0, 0, so that's the point I'm going to pick because it's the easiest one to pick. I plug it in. So 0 squared plus 0 squared, is that greater than or equal to 16? No. No, it is not. 0 is not greater than or equal to 16. I lost my or equal to symbol. That's just not true. So that tells me I'm not going to color in this area. This is not getting colored in. Instead, I'm just going to color in everything else. So, in doing so, it's going to look like the following. Which means, essentially, I should, once again, check my work by plugging in a point that's outside just to make sure everything works out, but this would be your basic answer to a nonlinear inequality. So it's basically same steps every time. Graph the equation, make sure, check whether it should be dotted or dashed or solid, then plug in a point and color in based on what you get, based on that result. That's it. Those are your steps. So as long as you know how to graph the original equation, that is the big question, then everything from there is fairly simple. All right. Now, what about systems of inequalities, though? Those get a little bit more complicated. We're going to start with linear inequalities. So here, the solution set of a system of linear equalities, just like the solution set to a system of a system of equalities or equations, is simply just the set of all points that work for both of our, in this case, inequalities. So, to graph a system of inequalities in two variables, we begin by graphing each individual inequality in the same rectangular coordinate system. Then we find the region, if there is one, that is common to every graph in the system. So this region of intersection gives a picture of the system's solution set. So this is all stated here once again. So here, what we're going to do is we're going to take these two inequalities, so y is greater than 2x minus 3, and y is greater than or equal to negative 5x plus 1, and we're going to graph each of them individually. So I'm going to start. Y is greater than 2x minus 3. I've already done this. We already know what this one looks like, so I'm not going to go through how to do this one, because it's exactly the same as the previous example. So I've got that. But now I have my second inequality. Y is greater than or equal to negative 5x plus 1. So I'm going to start by graph the y equals negative 5x plus 1. Notice that we're going to be doing a solid line because there's the or equal to symbol right there. So we've got negative 5 slope, positive 1 y-intercept. It's going to look like that. Then I check a test point. Doesn't matter where, just pick some test point. So in this case, we don't go through 0, or 0, 0, so I'm going to plug that in. 0 greater than or equal to 0 plus 1. Is 0 greater than or equal to 1? No, of course it's not. 0 is not greater than 1. So I'm going to end up coloring in the right side. Notice that I have colored in this area twice. That area is thus the solution to my system, because that is where we get solutions that work for both inequalities. Again, it is a very good idea to check your work here. Pick a point. Some point here, plug it into both, and see, does it actually work in both? So what point did I just pick? 1, 7. So this is the point 1, 7. If I plug in, that'll be 2 minus 3. Is that greater than 7? I mean, is that less than 7? So this is negative 1. Negative 1 is indeed less than 7. Check. Here I would get 7 greater than or equal to negative 5 plus 1. So is 7 greater than or equal to negative 4? Yes, it is. And so I know for a fact that this works both ways. And that's basically it for this whole chapter here. In some of the examples, you might come across systems of nonlinear inequalities as well, but it still works the same way. Notice that all of this works in a very similar fashion. Graph your equation, make it into the inequality form by picking a point, then color something in, see where the coloring aligns the end. So you will run into nonlinear systems of inequalities as well, but it's the same basic principles. So you'll see examples of this on the lab, etc.